Referring to our favorite, or at least our primary reference paper that we are paralleling in our efforts to model and then design a control system for a quadcopter, we're going to first simplify the model and perform a classical control system design so that we can not get lost in the state space representation and sort of trip over the math until we have a good feel for the physical reality and the sensitivities to some of our parameters and our drive inputs, etc. So we're looking for some transfer functions for roll, pitch, and yaw. And in our paper, here we have it. Now to get there, we need to make some simplifications. And in this video, I'm just going to go over a PDF that I'm also posting on the blog that covers how we achieve this statement. And bear with me, here it is. So our author, Bu Abdallah, claims that when A and B are the coefficients of the linearized rotor dynamics, while C, too small comparing to B, is neglected. Now in magnitude, that doesn't actually turn out to be the case, and I'm sure what the author meant to say here is, well, the sensitivity of the dynamics associated with C are negligible compared to B when we look at the differential equation, which is right here. So, So basically what he's saying, oh, that's not the Taylor linearized form. So we want to drop this term because this differential equation with the constant throws a wrench into our transfer function methods. So how are we going to do that? Oh, and for reference, I continue to refer to the Bu Abdallah paper, but this is it. You can find it referenced often and a link to it on the website, MT Wallets, but I refer to it as the Bu Abdallah paper because he appears to be the primary author. So how are we going to drop that C term? So we're going to look at the sensitivity to the small signal input, our voltage command to the motor that drive the propeller, U, and the nominal speed change, omega naught, which is in our C term. So here's our Taylor series linearized equation that we arrived at just as the author did, and we've got the A, B, and the C terms here. So first, let's get it out of the way where we confirm that the magnitude is not going to get us there. Define some constants. The battery stacks for these quad rotors I read is typically up to, say, 20 volts. So I just picked a mid-range voltage range of 10 volts from 5 to 15. I'm going to call that our dynamic range for the drive voltage for the purpose of this sensitivity analysis. The motor advertised velocity constant is 2,000 RPMs, and if you work through that, you get to a torque constant of 10 to the minus 2, and the units on that would be newtons per amp, or newton meters per amp. We cover dimensional analysis in a bit, just as a sanity check. So for right now, just take that as 10 to the minus 2. The units do work out, though. So there's an interesting equality. It's better explained in sources that we can look up, and there's a link to one on the blog. But the back EMF constant is equal to the torque constant. Units are different. In magnitude, it's the same. And again, dimensional analysis, it'll all flesh out later. We're going to assume a drag factor order of magnitude from our earlier efforts, 10 to the minus 6. And if we recall the drag factor, that's going to be a torque per radian per second squared. No gearbox, so the gear ratio is 1, the gear efficiency is 1, and also because J is common to the denominator of both B and C, it doesn't matter what we pick for it, so we'll just set that equal to 1 as well. Internal resistance for the motor, let's just assume that's 1 ohm. That's in the neighborhood. It's probably smaller for these motors, but we'll pick 1. And this gets us to, there's one more assumption that we needed to make for omega naught, and I'll cover that in a bit, but we do have an estimate for an average angular velocity for the propeller, and we needed that for the C term. But in any event, when we crunch those numbers, we come up with B is 100th and C is 600th. So C is not smaller than B, but again, the magnitude isn't what matters. We need to look at the sensitivity of the differential equation, the acceleration of the propeller, relative to voltage input, small signal change, and what is going to be, this is our non-linearized equation, but what's going to be a change in omega impacted by, then multiplied by this drag effect. So what are the dynamics, the small signal dynamics, when we change the drive voltage by a bit, and likewise how that's going to affect the dynamics introduced by this term, and which one's larger, and can we ignore one or the other one, or make a claim to do so anyway. So the first thing I'm going to do is look at, no, I'm sorry, I didn't really get to the sensitivity yet. The first thing I'm doing is establishing a range of angular speeds given a range of input voltages, which we established here. So, well, when the 5 and the 15 volt. So our lower angular steady state angular velocity is going to be the value at what is 5 volts, which we set above. And then the upper range is going to be the steady state value at 5 volts. So again, steady state, so we set acceleration equal to 0 and solve for omega. And this is what we come up with. So that's going to be our speed range, steady state speed range for that voltage range. Now we needed no omega naught for that C calculation we made above, and so I just took the average of these, and that's what I used up top. So this is what went into this estimate right here. So that value was used there. Okay, so we established our range, 5 to 15 volts. This is our range for 180 to 340 radians per second would result. And now let's look at a fractional step over that range that would represent small signal. So we take the step size as 1. That means that the first step is going to be the smallest step. And then I created a vector of successively larger steps up to 10. So we can look at, well, okay, is a 10% input change, a 20% change, 30% change? Where is this point at which we would not want to call it small signal, and we perhaps could not ignore the drag effect, and hence the C term. So the first thing is revisit the linearized speed equation. That's this one here. And if you recall, this is our A term. This whole thing here is our A term. This was our B term. And this is that C term here. So to perform a sensitivity analysis, we want to take the partial differential equation, the partial derivative of this function f, which is just the acceleration equation. And we want to take that with respect to, or I take it with respect to omega naught, because that, although it is in a constant, it really is changing. We're going to slide its value over as we operate over a speed range. So you can think of it that we're looking at a, we've linearized it, and we've thrown an omega term into a constant, but we're really going to update that over the range. And so what I'm doing here is saying, well, let's look at the sensitivity of this equation to changes in that parameter. When I take the partial derivative, we can see here this goes away. This drops out. This term here becomes 2d omega over nr cubed j. And then again, we got nothing here when we take the partial derivative, and this becomes 2d omega naught over nr cubed j. Well, we're talking about small signals, so we're going to take that omega naught minus omega. If you think we're stepping from where we are to where we're going to end up, that's a delta omega. So I just call that delta omega. So the resultant partial derivative is 2d delta omega of nr cubed j. So here, this is pretty straightforward. We're just establishing a vector of steps. So this would be a 1 volt step from where we started, a 2 volt step, a 3 volt step, a 4 volt step. And one or more of these is going to become for us what we will call a fair small signal. Likewise, we're going to calculate a delta omega that would be the steady state result for each one of these steps. So we step 1 volt, our delta omega is going to come up as 20. We subtract our low because we're starting always at our nominal omega L, omega sub L, nominal 180. So we started sort of, at 5 volts, if you recall. So we're starting from a non-zero operating point in the mid-range. So what that says is, okay, we stepped 1 volt, at steady state that we'd have gone up 20 radians per second. 2 volts, 40, and you can see here, all the way up. It's nonlinear, obviously, because of that that square term. And this tilde is just a Maple software trick for element by element operation. So there's no magic math in it. It's just a software tool. So now let's look at the sensitivity to small signal omega sub 0. So when we multiply that delta omega to assess the sensitivity, we're going to multiply the partial derivative by a delta omega, and so we end up with a delta omega squared, right? So it's this times delta omega. That's where we get the delta omega squared. And when we do that, this is the sensitivity of the differential equation here. The sensitivity of f to delta omega is here. Okay, a bunch of small numbers. We're going to look at it as a ratio, and then it'll make some sense. So now similarly, we want to estimate the sensitivity to small signal drive input changes. So we take the partial with respect to u, and when we do that, it looks a lot cleaner. We get that, and you can see it here again, partial derivative of f with respect to u. All this goes away, and we end up with just kt over rj. And so that's how we got to here. So now we're going to multiply that partial derivative by our delta u at each step size that we're considering to get the sensitivity of the differential equation with respect to u. We get more relatively small numbers. Not quite as small though. And we'll look at it as so let's look at it as a ratio. So if we take the sensitivity of the equation with respect to that voltage input over what would result as the change in angular velocity, although it's not, it's dynamically changing, but nonetheless, what we get is, by about a factor of 10 at 1 volt, we are more sensitive to the voltage input change than the resultant change in angular velocity that manifests itself through the C term as the dynamics of the drag. So the dynamics of the drive are 10 times more significant than the dynamics of the drag for a 1 volt step. For a 2 volt step, 6 times, 3, 4 times, etc. So that's what we're saying here. And this drives to a conclusion that we can ignore the drag-related C constant in our simplified model that we require for the classical control design. So there's one more adjustment that I claim we need to make, and that is in the paper, when we make that simplification to drop the C term, we are going to need to lose that 2 in the A term. And here's why. If you just back up again and examine, here's the equation reprinted. This is our linearized equation. What's happening here? If you think for small signals, omega naught, omega sub 0, and omega, they're real close to each other, right? So omega naught times omega, it's close enough to omega naught squared for a small change. So what we have here is, this is like a minus 2d omega naught squared over nRj cubed, and then we're just adding back a d omega naught squared over nRj cubed in the form of the C constant. And here I rationalize that when we make this assumption for a 1 volt, even at steady state, the resultant delta omega result from 1 volt step change would, jump us from 260 radians per second to 280. And if we look at the ratio of making the assumption that 280 is close enough to 260 and we just square it over keeping it actual and performing omega naught times omega, we're within 10%. So whether or not that's necessary, I did it anyway, and that looks like we're close. So that's how I'm able to back up and look at this and say, well, wait a minute, this is 2d omega naught squared minus 2d omega naught squared plus d omega naught squared. So wait a minute, if we're going to drop this term altogether, then we are, by a factor of 2, overestimating the impact of drag on what you can call the natural response. What do I mean by natural response? If you drop C, so get rid of C, and let's say we're running with some voltage and we just turn the switch off. What this tells us is the propeller is going to decelerate, and that makes sense, right? And it also makes sense that one element of the deceleration, there's the motor element of the deceleration, but there's this drag effect of the propeller that's going to decelerate us. But if we're not adding back one of these, we shouldn't have two of them in here. A multiple of 2 on the drag effect. So after we neglect that C term, I'm going to adjust that A term and come up with this simple differential equation for motor speed, and I'm going to call this valid sort of in the from 0 to a couple of volts based upon this ratio. So from up to a couple of volts, we're 6 times more sensitive to drive input change than we are drag change. So this is the simplified equation we're going to use. And then when we get into the controller design and then evaluating it and actually assessing the performance, we're going to look at the small signal performance and see how this all plays out. So having done all of that, I'm going to make a humorous observation, or at least it's funny for me. Before the Taylor series linearization, this was our original equation, right? So before we did all that fancy math and did the Taylor series linearization to get rid of this omega squared term, this is what it looked like. But after going through all that and thinking about this here, you know, that this is a small step change for the squared value, you know, by inspection, we could have just sort of called something an omega naught, and we'd have ended up with our simple, we'd have done minus d omega naught over nrj cubed times omega. This stuff would have combined into the A term. We'd have our B term, same as this, and we'd have been done. Now, I don't think that would have been obvious to me had I not gone through all of this. Probably would have been obvious to many others, but in any event, this gives me some confidence after just looking at by inspection. We sort of get to the same place, and that makes me feel confident in what we've done. And as a closing note, I did graph that ratio of sensitivity, and you might think that, well, heck, we could step 5 volts. That's 25% of 20 or half of the dynamic range we chose, and we'd still be, you know, according to this math, 3 times more sensitive to the voltage change than the drag effect. But I'm not sure about the validity of that, and I'd rather live up in here initially from 1 to 2 volts. I'll find out when we build something what we can assess down in that range, and then maybe we'll revisit this and see where we get. But that is how I resolved the confusion from the paper, from the Wu Abdallah paper, on what is required to neglect the C term. Through it all, made one additional observation that's not in the paper, and I'm going to run with this.